everyone, this is a continuation of the last video that we just watched. We're going to go over glomerular filtration just a little bit more and then dive right into tubular reabsorption and tubular secretion. So once again, glomerular filtration, we are pushing whole blood into this really small cramped space, and that is forcing plasma out into the Bowman's capsule. So there is that fluid pressure, that filtration pressure, which is forcing it out, and in the end we get a fluid called glomerular filtrate. So filtration pressure, it is kept high thanks to the capillary bed structure because it is a very small space and there's a lot of fluid going in there. There's a ton of pressure squeezing that fluid out of the capillary space and into the glomerular capsule or Bowman's capsule. So the pressure overcomes osmotic pressure. Normally osmosis is going to make water go from high to low concentration, but because there is so much pressure due to the blood and blood pressure and the heartbeat and the heart rate, that's what squeezes ultimately a lot of that fluid out instead of having it all be recaptured again by those plasma proteins. So the net filtration pressure takes into account all three of those factors, the osmotic pressure, the blood pressure, as well as that hydrostatic pressure being in there. And we can see all of that over here to the side. So the rate of filtration, I also want you guys to think about the afferent and the efferent arterioles. So the afferent arteriole is where blood is going into, or how it gets into the glomerulus, and the efferent arteriole is how it leaves. So these two arterioles are controlled by either vasodilation and vasoconstriction. If we are constricting blood flow, that is going to increase the pressure because it's now in a smaller space. Whereas we dilate it, it's going to decrease the pressure. So this is showing vasoconstriction, it's dropping, it's getting smaller, vasodilation, it's increasing. Whereas the efferent, it's going to, the constriction is going to increase that pressure and the dilation is going to decrease it. So why does that happen? Efferent, it's going towards it, right? So if the efferent arteriole constricts, that's going to lower the pressure within the glomerulus because we're not getting as much fluid into it. If the afferent arteriole dilates, then that's then going to allow more fluid into the space. So that is going to increase the amount of pressure in the glomerulus itself. Now the efferent, as it constricts, that's going to limit the flow of blood leaving the glomerulus, so that is going to increase the pressure here. Whereas dilation is going to lower the pressure because now we're getting more fluids out. So this is all super kind of confusing, but this is once again where you can start to tie in the cardiovascular system with the urinary system. It is also controlled by the colloid osmotic pressure. So we talked about the albumin plasma proteins a while ago and how those will help regulate body fluids. So the plasma protein concentration, those albumins, that is going to be inversely proportional to the filtration rate. Because we are looking at more of those proteins is going to have less of that filtration. We're collecting more of that fluid back in. So if we have a lot of plasma proteins that are staying within the capillaries, we're not going to get out as much. And finally, that hydrostatic pressure, that blood pressure. How hard is the heart beating? If blood pressure is really high, that's going to force a lot of this fluid out and into the glomerular capsule. Now, we end up seeing some issues sometimes with really high blood pressure, causing issues with glomerulus breaking, and that is something that you can really start to talk about later on with renal failure. So, the regulation of filtration. We have the sympathetic nervous system, which is going to be activated. Remember, sympathetic nervous system is the fight or flight, and that is what can help alter the dilation and constriction of those arterioles. Natural atretic peptide. We talked about this a while ago within the endocrine system again, and this is what's released from the atria of the heart. You guys might remember that. And that is going to lower blood pressure. And the way that it does that is it increases your filtration rate. So this is yet another connection that can be made with the circulatory system and the urinary system. So that hormone is secreted by the heart. It increases that filtration rate, which means that you are now getting out even more fluids, ultimately lowering your blood pressure because there's not going to be as much fluid in your blood. So, renin, we talked about this in the last video, and I'm going to continue talking about it here. Renin is going to be secreted when the afferent arterioles sense blood drop. So the afferent arterioles are going to the glomerulus. When they sense blood pressure dropping, we are going to secrete renin. So this is another sympathetic nervous system response. Those macula densa, which are around the distal convoluted tubule, which we have not yet talked about, is going to sense the decrease in chloride, potassium, sodium in that tubule, and ultimately is going to cause renin to be converting angiotensin 1 into angiotensin 2. Angiotensin 1 is then converted into angiotensin 2. And then after that, we end up secreting aldosterone from the adrenal glands. Oh my gosh, that was a big pathway. So we go renin, angiotensinogen, angiotensin 1, angiotensin 2, and eventually aldosterone. And hopefully you guys remember aldosterone from the endocrine system. It absorbs sodium and secretes potassium. Now when I say absorbs sodium, we're pulling sodium out of the urine and into the bloodstream, and we are pushing potassium out of the bloodstream and then into the urine. You guys might also remember water follows salt. So if you are taking sodium out of urine, you're also going to be pulling water out of urine. And the more water you pull out of the urine, the more water is going to be within your bloodstream, which is then going to cause your blood pressure to increase. The more fluid you have in your blood, the higher the pressure of the blood. So this whole thing all over again, and this is going to be really, really important for one of those concepts, so I really hope that you guys get this. Renin is going to be secreted when those afferent arterioles notice your blood pressure drop. It raises your blood pressure, so it helps maintain homeostasis by causing angiotensinogen to convert into angiotensin 1, angiotensin 1 to angiotensin 2, angiotensin 2 to eventually secrete aldosterone. Aldosterone pulls the sodium out of the urine, which by osmosis pulls the water out of the urine, increasing the water within your bloodstream, which increases your blood pressure. Feel free to go back and watch it as many times as you need. So, here's the whole thing in a nice little visual for you. Renin is going to be secreted when your blood pressure drops. Its function is to increase your blood pressure using aldosterone. I love, love, love this picture. Feel free to use it as many times as you need. So now, we've already talked about glomerular filtration rate. Now let's go over tubular reabsorption. So we're going to be doing reabsorption 3 different ways: diffusion, osmosis, active transport. So we're really big into active and passive transport from earlier in this year. Proximal convoluted tubule. So we've gone into the glomerulus, we've filtered stuff out, and now we're in that little tube. It is surrounded by the peritubular capillaries. So remember, if we're reabsorbing things, it's going from that tube into your bloodstream again. The proximal convoluted tubule is going to reabsorb all of those things listed right there: glucose, amino acids, creatine, lactic acid, uric acid, absorbic acid, phosphate, sulfate, calcium, potassium. Sodium is moved by active transport. So a lot of these things are beneficial for you. I do not want to lose all of the glucose that I just ate in my kidneys because it went through that filtration process. So tubular reabsorption grabs onto all of that glucose, all of those amino acids that I just lost through the filtration process, and puts those back into my bloodstream so I don't pee it all out. Water is moved through osmosis. We go from high to low concentration. There was so much water that was forced out at that glomerular filtration rate that a lot of it is eventually going to be pulled back into the capillaries because of high to low concentration. So this is everything nice and spread out. Oh, I love this picture. It's beautiful. So we have the afferent arterioles going into the glomerulus, and then the efferent arterioles taking things away. We have the glomerulus, Bowman's capsule. Filtration pushes all of that stuff out, and this is our glomerular filtrate. All of that is going to go into this little tube right here. Now, once again, if it's in the tube, it will become urine. So we pull that stuff that we want, including sodium, potassium, glucose, amino acids, out of the urine and back into our bloodstream into those peritubular capillaries. This is all happening within the cortex of the kidney. So we slice the kidney open. You can see like there's a darker region and then the lighter region on the outside. We're on that lighter region on the outside. And then we get down into this thing called the loop of Henle. This is where we dive down into the renal medulla. So this is within those like renal pyramids. We're going to have more stuff be absorbed out or reabsorbed into the peritubular capillaries, and the reason is because of osmosis. Those medulla pyramids are really, really dense and full of like proteins and other things, and so that's what ends up drawing the water as well as the sodium, the potassium, all of that stuff out. The farther down you go, the more concentrated it gets and the more water is pulled out eventually. So continuing that peritubular absorption. Sodium is going to be actively transported. So we go through actively transport. We have those windows that facilitate the diffusion, and that is going to call those other negatively charged ions, because sodium is positive, so the opposites attract thing. We're pulling out those negatively charged ions to be moved out passively. So we're only spending energy on pulling out the sodium. Once those negatively charged ions come out, then water is going to follow thanks to osmosis and also that concentration difference within the medullary pyramids. Now, sodium and water reabsorption is going to continue along the proximal convoluted tubule and that loop of Henle that dips down into the medulla. So here we have the glomerulus, the proximal convoluted tubule, because that's closest. So when we're looking at closest, we're looking at closest to the glomerulus. The loop of Henle, which is going to dip down, and then the distal convoluted tubule. So, limited transport capacity. We only have so many carriers for transport. So if the concentration is below renal plasma threshold, the carriers are going to reabsorb all that they possibly can. This means is that if we don't have much of that substance, let's say we don't have much glucose in our blood, your carriers are going to be able to pull all of that glucose back into your bloodstream. Now, if you have a ton of glucose, like people that have type 1 or type 2 diabetes in your blood, then your transport carriers are not going to be able to get everything, meaning that a lot of that glucose is going to stay in the urine, which is one of the biggest symptoms of diabetes. We end up having frequent urination as well as that sweet smelling urine if it is a really, really extreme case. So, tubular secretion. Now we are getting rid of a lot of those substances. So we're in the capillaries, the peritubular capillaries, and we're going to start dumping stuff out and into the distal convoluted tubule. Your body is actively going to secrete penicillin, creatine, histamine, which is one of those amino acids, hydrogen ions, and potassium ions. The hydrogen ions is how we regulate your pH, your blood pH and your urine pH. And the histamine, once again, is going to be secreted. Creatine is going to be one of those waste products by your muscles. We talked about how creatine ends up supplying that phosphate on for the ADPs to supplement ATPs. So all of that stuff is going to be secreted in those tubes. So once again, big overview here. We have glomerular filtration, tubular reabsorption, we have the loop of Henle, which is going to have a lot of that absorption, and then normally tubular secretion is going to be left for the distal convoluted tubule. Everything that's left in that tube is going to go into the collecting duct, eventually into the renal pelvis, and then be secreted at the very end. If you have any questions over this, feel free to stop, rewind, and go back, or feel free to contact me and we can go over this again more thoroughly. I hope you guys have a great day. Bye.